Okay, so it's already 3. I think we should start with our presentation. So, good afternoon, ladies and gentlemen. I am Aniket from EDS Technology, and I would be your host for today's webinar. So, first of all, I would like to thank each and everyone for taking out their time and joining the webinar, ensuring automotive compliance with CAVA. So I would like to introduce everyone to Mr. Chandrakant Akhade. So Mr. Chandrakant Akhade, he has 18 year of experience in CAD and PLM application. He has an extensive knowledge and has successfully managed numerous CAD and PLM projects across various industry verticals. He adapt at maintaining a high level of customer satisfaction through long-term customer partnership and delivering exceptional service and support. So I asked Mr. Chandrakant to give the short brief about EDS technologies and corporate EDS technologies corporate profile.
Thank you. Thank you, Aniket. Hope I'm audible to all.
Yes,
Okay.
yes,
So
you are
talking
audible,
about
sir.
EDS technologies, today we are the largest PLM solution provider in India for close to 3 decades. We are present almost around 10 locations pan India. Our headquarters are in Bangalore, and we are almost 200 plus associates, and we have 2000 plus customers across pan India. We are supporting. Just to mention you, as said earlier also, EDST journey started in 1994 with a business partnership of Deneb Robotics, Deneb Digital Manufacturing Solution, ideally it is called as, and it was our own company started in 1985 by our investors in USA. So Dassault Systems thereafter acquired Deneb in 1997, and this software was re-christened as Delmia with DS portfolio. So in 1998, we became first partner of DS in India for their flagship product, Katia. Since there is no looking back. Today it is pretty long relationship, almost 25 years plus with Dassault Systems, and we are the largest and platinum partner of DS in India, and also ranked among top 10 partners across DS worldwide. So as you can see on the slide, these are our core business solutions. Our organization is spread across 9 different business solution, starting with virtual twin, which is largest offering solution primarily from DS 3D experience platform, along with strategic products like Q Checker. That is what from Technia we'll be talking about CAVA in detail going forward. We also are partner with Humanetics for Ramsys, and we under business consulting we provide 3D experience consulting implementation services for entire end-to-end PLM roadmap that customer has. So apart from that, we have from electronic design automation tools, typical tool like Synopsys from USA, and 3D printing for both metal and polymer printing from EOS Germany. We also represent primarily geospatial intelligence through GIS application called ISRI, and we are also in optical solutions typically going forward now. So in brief, just to talk about EDS, this is our USP. We have been serving the industry from last almost 30 years now. I am closely associated with EDS now almost for 18 years. So we carry the legacy of supporting our customers end to end, shoulder to shoulder, till the problems are resolved, and we see how overall business solutions that customer procures from us, how it is really used practically, any issues are there, and they get a very win-win benefit of the solution that they buy. So that's how our motto is there across industry, across our business portfolio, to take care of our customers. So in short, I wanted to brief you about this from EDS Technologies perspective. I think we can move to next our speaker, Mr. Sushil Punaskar. So Sushil works as senior solution consultant, as you can see on the slide, for EDS Technologies, specialized for Ramsys, Q Checker, and CAVA solution. He has more than 22 years of industrial experience. He has worked with many major Indian and European OEMs. In addition to it, ergonomics perspective, he specializes in BIW design and development, composites and carbon fiber BIW design. So I think we can start with Sushil. Yeah, over to you. And then, okay. Yeah, sorry. So Satyam is next our speaker. He's a application engineer in EDS technologies in our engineering solution domain. He is a technology expert specializing in CATIA V5 3D experience platform, Technia perspective, CAVA and Ramsys application from Humanetics. He has over 4 years of experience in industry, providing comprehensive support on all vehicle packaging, compliances, ergonomics, application to multiple customers. He leads workshop sessions for OEM suppliers, engineering service providers, and all academic institutions on multiple technology perspectives. Expertise specifically has in understanding and addressing client needs across diverse sectors. So this is content of the entire webinar today. We'll have CAVA from regulatory compliance perspective, how it can be used. It's basically introduction. And then thereafter, what all modules CAVA has, typically OVA, mannequin, vision, safety, wiper, as you can see on the screen. And end of the session, we'll also have a Q&A for interacting with your queries and all.
Thank you, Chandrakant sir,
Yes.
for this introduction.
Yeah.
I think these are the bold contents that we'll see today, one after the other. So we'll cover what CAVA is, what CAVA is known for, and how CAVA can help you do your early vehicle analysis quite efficiently, and then very confidently go for the next phases of development. So these are the bold contents. We'll cover regulatory CAVA for automotive regulations, introduction of CAVA. Then what 5 modules of CAVA we will cover, like OVA, mannequin, vision, safety, and wiper. And it will be followed by a demo, the tool demo from Satyam. And it will be followed by a Q&A session. So we'd like to take your questions as well. Okay, with this, let's start the discussion forward. Let's first spend few minutes understanding automotive compliances overview kind of discussions. So compliance, as you know, are highly critical in nature. They are too technical, and they shall be checked with utmost care and attention. Though they impact to large extent on the vehicle structure and vehicle regulatory aspects. And there are certain drawbacks out of it, like the manual methods that we employ in any companies. They are traditional methods, and they have certain drawbacks with them due to high speed, due to the lack of speed and lack of efficiency. So manual checks in native CAD application may be unreliable many times because they have some manual intervention in the middle. So there can be some untrapped or unchecked areas remaining without the notice of the engineer. For compliance checking, to understand compliances and do it efficiently in the native CAD is actually needs the skilled resource capabilities. So it's kind of a dependency built up on resource. Otherwise, it's actually dependency built up on the resource. So this activity shall be completely free from any dependency because it's looking at its nature of criticality. Manually checking in CATIA in any native CAD, UG or anything, it's actually time consuming due to absence of any automation tools, because there are certain automation needed in this safety regulations. For example, wiper needs a lot of automations. Any design change demand checking all over the again. You have to check any change in the amendments or any change in the design. You have to follow the whole process 1 hour again. So same amount of time is consumed again. The regulation, the results are not automatically available. It takes time to publish them. The engineer has to make some fantastic presentations out of it to showcase and convince that the compliance the compliance is meeting or not meeting. So it takes time to really publish the results confidently. Result statistics is not readily available. So actually it takes time. We cannot really see whether what zones of the data is really meeting the regulations are and what are not meeting the regulations. So that data is not really statistic available. In case there is amendment in the regulation, for example, any new amendments come to cover the global regulations, it needs doing it all over again. So that amendments also takes time to recheck again. With this serving the globally to all OEMs or something, it takes time because the checking itself takes time. So the quick feedbacks to the customers really can't go from outside, and that takes a lot of time to publish the results to the OEMs. So that with that, these all aspects of manually checking, CAVA can really solve all these complexities and get this completely de-risk the whole automotive regulatory checking as such, and just free you from all those headaches of knowing the kind of reading the regulations, understanding the regulations, and then doing it in the manually in CAD. So we'll start from this with this understanding, like CAVA is an abbreviation of a few terms, what we call as automotive extensions, vehicle, CATIA automotive extensions, vehicle architecture. So that's what CAVA stands for. That makes regulation standards and guidelines relevant for the vehicle concept as V5 features. So as you see in the picture, the CAVA is at the center, and revolving around is actually from the very far right, you have some architectural layouts that CAVA can support. Then to next is actually the bumper and hood and the fender regulatory zones for minimum radius checks. Then we have some vision and interior vision and mirror vision requirements in the CAVA. And also we have some wiper to be on the top. So CAVA can have all these checks right from the beginning up to the homologation stage. CAVA can support you with different modules, of course. CAVA can really start from very early phases of development, like from the layouting stage, when you have just SGRPs and layouts of the vehicle, and you have just CAS arrived, and you want to give some early feedback to the styling team, or to maybe the engineering team, or to maybe supplier team, and maybe safety team, whether the CAS is really compliant or not. So CAVA really starts from that phase, and it goes up to the homologation phase. It can support you all up to the homologation phase. As we see, CAVA has, as I said before, CAVA has different modules to cover the different areas and those many critical regulations. So first and foremost is the CAVA. What we are going to see now is the CAVA overall vehicle architecture. So CAVA has amazing features for architectural designs. So these are what we'll see that in the next couple of slides. So here's the road clearance surface, which is comprising the basic surface that you see in the yellow wireframe text. So that is actually readily available in CAVA with just few parameters, and this can be a excellent source of input to many underbody engineers, for example, the harness team and also the underbody team. We have altogether built SAE templates for mannequins, which you can place on the SGRPs on the front and rear passengers. You can really study a lot of amazing areas like knee room, leg room, head room, etc. As I said, mirror vision, rear view vision is actually one of the capability of CAVA. You can certify, CAVA can literally certify on the go whether this size of the mirror and with those adjustments, your mirror is really compliant with that regulations or not. Then there's a close range visibility, which depicts test specimens moving around the vehicle, test cylinders, and it can specify whether they are compliant from the visible from the seated positions or not. Then it has a field of view, which is where the whole vision criteria and vision classification starts from the vehicle interiors. So it can plot a field of view directly on the windshield. Then from that, you can also simulate CAVA wiper regulations directly on the windshield. And of course, there's a from the exterior side, we have pedestrian protection feature also that protects, that has actually the feature of plotting a lot of WAD lines, wraparound distance lines. It can also give you pedestrian offset zone also, that can be very helpful for the underbody engineers. Yeah, with this, I think let's move ahead. CAVA is equipped and built in a lot of national and international standards are there. And recently there are many AI standards also implemented in CAVA. So we have a Federal Motor Vehicle Safety Standards for North American region. We have Europe, Central Europe, and most of the Europe region is covered with the EC standards, MLIT, the Japanese standards, and of course the Australian regulations are there. So to name few, here are some samples given, like which are the regulation applies to which components. There are some rear view mirrors and of course seat belts, bumpers, some mannequin tools like ellipses and head forms, field of view, head impact. We'll see one by one as we go forward. So CAVA is built on one architecture, how to perform the CAVA studies in vehicle space or the digital space is basically starting with CAVA base data. We declare some parameters in the very early phase of the phase of the studies. And we start after the base data is created, we subsequently start the further studies, may it be on OVA or vision or mannequin or safety or maybe wiper. So creation of base data is the first and foremost important thing in CAVA to start the studies, CAVA studies. Interesting side that how does CAVA workbench look like? Now this is a CATIA integrated version. CAVA is integrated in CATIA also and in Annex also. There's integration available at the moment. And this is the far left is the how CAVA icon or the CAVA looks like on your dashboard or desktop basically. And the second image is actually where the CAVA tool or the CAVA workbench can be located in the workbench tools. And this is a typical CATIA V5 workbench with CAVA toolbars available on the go. That was a brief introduction about the CAVA workbench, how it looks like. It is not very different than the CATIA workbench, of course. Yeah, let's talk about the CAVA database. CAVA base data is actually, we can start the creation of the actually studies. We start with base data creation. For base data creation, we certainly need some important architectural inputs. Not all, but few may be certainly needed. First and foremost, like it is a passenger car or off-road vehicle, that declaration is really needed. Then you need wheel centers, front and rear wheel centers locations in vehicle space are required, and tire radius, tire radius and tire static radius are required. Gross vehicle weights, GVWs, curb weights are required to be declared. Not absolutely mandatory, but it's good to have. Then seating reference points, accelerator heel points, seat travel, and pedal reference points, or we call it ball of foot, that is required to be declared. And seat back angle, that is also required to be declared at the beginning. With this base data creation, we move forward and we perform individual studies in CAVA. So first is actually the vehicle overall architecture. I think before we jump into the detailed technical discussion, let's take some use cases, typical safety cases where CAVA can support you and how to do a better engineering. So let's run the first one. It is actually about so this is the active hood and the pedestrian injury. How does the pedestrian leg impact and knee impact and also the head impact is for the adult is performed. This is a realistic demonstration, but the same can be also done on CAVA. So here the presentation was with the active hood. There is a possibility in CAVA to simulate the active hood capability also. In the second, we will see how does the side pole impact test is happening here for the two competitor cars, and the structural performance is checked. But here the takeaway point is the location of the impactor with respect to the vehicle SGRP point is very important. So that CAVA can support you that where does the impactor and the pole is located in the vehicle space, so that the structural performance of the door shell and the door intrusion beam can be really ensured in that way. With this, let's take one more thing, like it's very interesting for the bumper design, maybe for the exterior design. There's a car coming up with the certain bumper conditions here, and it is clashing with the leg form, the knee form here, and it has completely cramped and the deformed hood. So that means that it has injured the pedestrian quite a lot. It looks from the deformation that the pedestrian is really impacted a lot. However, if you see the right bottommost vehicle condition here, if you see closely, it is quite different than the first one. There's the impact absorption here. Now that has all been done with the help of position, intelligent design in the bumper, and the position of this knee with respect to the bumper here. So that's how we nowadays, if you see this type of hood is actually nose is called soft nose design. And that's how we see many car makers now are going ahead with the front bumper with the soft nose designs, which is actually keep with the context of minimum injury to the pedestrians. So CAVA can simulate this, the location of the bumper, this knee impactor, so that you can do intelligent designs in the bumper, like the position of the foam here, the impact absorption foam, so that there is a minimum possible injuries to the knee impactor here. Here we start our real discussions like from the OVA, overall vehicle architecture. CAVA can readily, as you see, CAVA can readily create a lot of interesting surfaces for front approach and departure angles. This is approach angle. With the given base data creation, it can certainly create front approach angle. Now, there can be different tire combinations in a vehicle like R14, R16. So you have to take all this into consideration, and you can derive two type of approach angles, so minimum to be possible to be adhered. So these surfaces are readily available to the engineering team, bumper team, also to the front-end engineering team as a ready surface, so that they don't cross these restrictions, the architectural restrictions. Static curb radiuses and static curb heights are automatically created in CAVA. So with the given base data, it can create a surface altogether with a curb. Curb is where we go on the curb and strike that. So there is a possibility to strike the curb, and the bumper has to be, the certain vehicle details has to be protected against the curb strike. So CAVA can generate these surfaces readily on the go, so that none of the body engineering or vehicle engineering crosses that limits, and then thereby there's no chance of any impact in the road vehicle. Front and rear, like even the approach and the ramp or angles are possible to create readily in CAVA. So you can create these surfaces, very important for the underbody engineers and also for many other purposes. So the beauty is that it's available as a surface, so that surface can really be referred by many engineers for their day-to-day activities for the underbody engineering. Maybe it can be some pneumatic piping, it can be some harness routing, or maybe some other purpose. So these surfaces are really important. Ground clearance studies with the given condition and with the given regulation, we can really create a ground clearance reference zone. Again, very important for the underbody engineers for many purposes. Maybe the bottommost points shall not hit any stone strike, or maybe the road surfaces, so that the ground clearance surfaces are readily available in CAVA. It can be made available to many other architectural engineers, especially underbody engineers are mainly interested in this. Oil pan clearances, like now with we have still some ice cars, like internal combustion cars, where the oil pan clearances shall be protected, because it should be more, the oil pan's height should be always more than the ground clearance. That's but obvious. So these surfaces shall, however, be readily available to all the underbody engineers, especially the front end engineers, to know what are the different clearances, and they should have some certain clearances from these limiting zones. So this can be readily available, and they can adhere to it, so that we don't disqualify these particular regulations. Uh, this is actually very interesting, where we, in the finished good condition, when the vehicle is left the company and it goes to the dealer, it travels along long distances actually. so that it needs to be secured in certain way. So certain areas on the body shell or the underbody shall be always free from any undulations and any obstructions and distractions here. So that the Kava can really plot the surfaces directly on the underbody, and it can give you surfaces where the body shall be completely free of any obstructions or hindrances, so that the car can really travel in the most efficient way to the dealer without any damage to the vehicle. Since it's a finished good inventory, it should be protected in the best manner possible. Water wading levels and water wading heights zones can be plotted right directly in the Kava. Very important to know. Now, normally 300 millimeters of water wading depths are usually protected for any vehicle. However, in North America, this is around 400 millimeters water wading depth, so more than 1 feet. So these water wading levels are readily available, so you know what is your wet zone and what is your dry zone. So certainly this is very important for the corrosion protection engineers to know this, what is dry zone and wet zone, so that certain extra protections can be done on the underbody in the wet zone area. So Kava can plot this very readily on the go for you. Lamp position certification specifies that the lamps and the illuminating surfaces actually are placed with respect to with some height from the ground and inboard from the extremities of the vehicle in certain way. So these vertical and horizontal lines basically are readily plotted in Kava, which gives you an indication that your lamps shall reside or shall be located in this zone only. So that's how we meet the lamp certification. It can also check your existing lamp position and also certify that whether it meets the regulation. For example, EC is a European regulation R48 revision 4 number. So it can certify whether the lamps are meeting this regulation or not on the go. So you have a digital confirmation directly in the Kava. So you did not look to refer any altogether EC regulation standard, which is more than 100 pages altogether to read. But it can certify, Kava can certify this directly on the go in CATIA tool, in the Kava tool. And especially the lamp position is of high importance because it has a very high critical impact on the underbody front end engineering and also the packaging, because the housings of the headlamp quite protrude on the backside quite long, and they consume a lot of space on the backside. So it's good to certify the lamp positions from the very early stages of the development. So Kava can very quickly simulate and certify your lamp positions directly. A lamp, just like positioning, lamp visibility can also be certified in Kava, very importantly, so that you know what are your reach zone areas and illuminated zone areas. So Kava can certify on the go your lamp positions also and the visibility also. Yeah. Number plate, again, number plate different from different continents like European, American, Asia Pacific. We have different regulations, and for the number plate positioning, so it shall be positioned in certain height and certain width, and the minimum possible distance from the ground plane. So all that can be readily checked in Kava, depending upon different regulations it has certainly. So this is again a very important. Otherwise, it takes a lot of referring to European standards or American standards, federal standards, to know what are the minimum ground heights the number plate should be located from. So Kava does it very efficiently, quite efficiently, quickly also. Number plate certification. As I say, whenever bumper skin is released from the cast, the first and foremost activity that many bumper engineers do is to certify it for many regulations, for approach, for maybe for leg impact and etc. So Kava has a tool to certify your bumper designs. It checks these ECR42 regulations quite efficiently, and it can certify your bumper designs on the go, whether there's a certain areas of the bumper are quite intelligently placed so that there's a minimum impact to the knee, etc. Also, Kava can also place and package and give a very probable location of the bumper beam, which is the crash beam in the vehicle structure. So it's very important location. This is quite important for meeting many crash regulations. Uh, if you move the bumper beam quite somewhat top or bottom side, it completely changes the crash behavior of the vehicle. So it has to be completely and quite efficiently placed right from the beginning so that you meet those criteria also, crash criteria. Side impact, what the movie or the video that we saw in the very first slides was actually the pole impact on the side, from the side. So knowing the pole position with respect to the SGRP is of high importance, then because then only we can be really doing our body engineering and door engineering quite well to protect that against this impact. Uh, as you know, the side impacts are very crucial from the front impact, because the location of the impactor from the mannequin is quite close than the front impact. So intelligent body engineering should be done to avoid any intrusions. So we can really engineer our intrusion beam designs accordingly if we come to know the pole position with respect to the SGRP. So we can create surfaces directly on the CAVA and give to the door team so that they can always refer to it and do their body engineering accordingly. Wheel covering, as you say, is again a safety feature. It's a regulatory feature with some regulations in Europe and India also. If you closely see from the front side, if you see some portion of the bumper is always covering the tire from on the top side. So the tires are actually go inside the fender here, with some reason of safety. So the pedestrian should not get injury by any rotating tires and etc. So this regulation is actually can be the triangular zones or the limiting zones can be readily calculated in CAVA. Very important for the fender engineers and also for the bumper engineers also. Seatbelt, as I said, seatbelt can be seatbelt zones are regulatory zones. Top anchorage and bottom two anchorages are actually come under regulation. So a body shall be protected for that, and architectural, it's a day in day out job of architecture engineers to ensure that the anchorages are certified and the location is also certified. So CAVA can really give you different zones of top anchorage. The full zone is given so that you can literally choose which works best for you. Maybe there can be some zone here, but your B pillar can run from here. So you can literally choose a different zone. So knowing these surfaces is really good practice and it's high importance for body engineers again, side body engineers. Know these surfaces, where to locate our bump anchorages. So CAVA can give you this ready-made zones on the go. Also for the rear passenger and for the child also, it can give you tethering zones and protection zones where you can make use of. Pedal clearances, there are CAVA can support you manual transmission and also the automatic transmissions. It can certify your pedal geometry and the footwell geometry quite efficiently, whether the pedals are of certain width and certain space with certain spacing in the between. So it can give you a very color coded graph like which dimension is meeting and which dimension is not meeting. So then you can take necessary action to place them accordingly. Otherwise, manually doing this is quite a consuming job. I mean, there can be some engineers who don't know how to measure the normal distance here, so he can pick any random point and choose incorrectly. So CAVA actually completely takes care of that risk of any manual intervention and manual errors. Yeah. That was mostly CAVA, mostly OVA, overall vehicle architecture. We'll start CAVA mannequin here. Like the first one is availability of ready-made availability of ellipses from the seated position. Now, knowing ellipses and creating ellipses is a quite time-consuming job in native CAD, maybe CATIA or Unigraphics. So CAVA, just with the base data, you can readily create the ellipses, which can be further used for many vision studies like apilar obscuration for forward visibility and also the side visibility also. Again, head impact zone also can be created equally well in CAVA, quite fast with the creation of base data, so that you know what are your head roof geometries are very close or not. So these surfaces can be exported to the interior engineers who are actually working, maybe roof engineers or maybe the headlining engineers also, to know these surfaces. And this becomes very important to know head position contour when you have height adjustable seat designs. There is certain Z travel on the seat, so you can literally take these values also and play and set up your roof structure and roof outlining accordingly. In the seat, there are some criteria like the seat restraint, head restraint needs to be certified for certain height and horizontal distance criteria from the mannequin head. So FMVSS 20A certifies that or states that requirements. So CAVA can, in the seated position, CAVA can take your head restraint geometry, and it can certify that it meets certain regulatory criteria. Henry zone, very important for the IP and cockpit engineers to place their controls and utilities and buttons and etc. and infotainment system, so that it's like a haptics and it's a touch-worthy points on the IP and cockpit. So CAVA can give you three Henry zones according to SAE J287 quite quickly. So it's a three-finger zone, like to operate some radio buttons or maybe temperature control on the heating system or cooling system. It gives a hand grasp, full hand grasp zone also, and extended finger also. So there can be some push button kind of thing. So that is usually operated by one finger. So that's called extended finger grasping. So with these three readily available surfaces, there is no ambiguity at the mind of the cockpit engineer that which controls are within reach and which are not within reach. With that, let's take some look at what are the CAVA vision capabilities in CAVA vision. First and foremost, where the CAVA vision study starts is the creation of the field of vision. So with the seated position, with the declaration of the base data, CAVA can plot these vision cones directly on the windscreen, which is a start point of wiper calculations directly. So certain areas of the windshield should always get wiped from the regulatory position, from the seated position. So CAVA can certify, CAVA can plot these tools on areas directly on the windshield, yeah, which are subsequently used for the wiper simulation also. A-pillar obscuration, it's like a blind spot identification. It's a regulatory element again. The A-pillar should not cross certain angular and binocular obstruction, angular obstruction, so that there is a risk to the that missing the outside pedestrian or pedestrian object, and thereby driving over it. So this binocular obstruction has a limit of 6 degrees according to regulation. So CAVA can take your A-pillar geometries and also trim geometries, weather strip geometries, and everything, taking everything into account. From the seated position, it calculates the A-pillar obscuration angle. It gives the angular value that what is the current angle value, obscuration angle value. It's very important because it's a blind zone for the driver. As I said, mirror ORVMs can be certified directly in the CAVA. You can give all your inputs to the like what are the adjustment angles, for rotation angles, and nominal positions of the mirror to the CAVA, and it can certify the CAVA geometries, the mirror geometries accordingly. So the left one is actually the actual test being carried out on the wall method. So wall method is actually the preferred method of certifying mirrors. But there is another method mandated by regulation is the floor method or the ground method. But ground method is not normally used for certification. Mostly the wall method is only used. So CAVA can literally mimic this physical test regulation, the physical test procedure directly into CAVA. So if you see closely, this quite resembles to each other. CAVA can, this one of the best feature of CAVA to directly on the go, it can certify your mirrors. So that if any if the mirror geometries are not within any specified dimension, then there can be some indication like we need to increase our glass mirror size, or else we have to change the anchorage points or hinge points, something like that. Mirrors, CAVA can also is a possibility to simulate reflection analysis on the windshield, because reflection is actually an annoying phenomena in the interiors. It can be daytime reflection, it can be night reflections, but they are dangerous. So technically, whatever on the IP or cockpit, everything is capable of getting transferred and reflected onto the windshield. And however, we should always package our positioning of the controls and buttons, etc., quite intelligently, so that at least they are not in their visibility zone of field of vision. They are away from that. So this study, however, is very important for the architecture engineers to perform this reflection analysis, so that there is no surprise when the vehicle is put to the condition. As I said, close range visibility is that it places some test specimens resembling child occupants, child pedestrians, and certain zones of the child should always, or the cylinder should always get visible to the driver from the seated position. That is the condition put forward by the regulation. So CAVA can certify this geometry, this regulation automatically in this close range visibility module in CAVA. There's something called GCI, Global Car Information Exchange Forum, where we actually we can compare our or we can know that how far we are the vehicle 360-degree wise visibility, how much is the percentage of blind zones on our vehicle. So CAVA can take the whole car geometry and the daylight openings without the glasses, of course, and it can give you this pie chart. It's not pie chart; it's actually visibility zone with the blind, with the red sectors representing the blind zones from the vehicle, from the driver space, driver seated position. So CAVA can plot this uh, uh, plan view, what we call, and also it's helpful for comparing benchmarking purpose also. I think let's move to safety, which is actually one of the top module of CAVA. It's highly recommended and highly used worldwide also. It has certain features that are outstanding in nature. Like the first video we saw, the very first of the presentation, we saw one video with the dummy hitting the head on the hood. So CAVA can generate that WAD lines, wraparound distance lines on the hood. It can bumper line, lower bumper, upper bumper, hood lines, etc. And apart from that, CAVA also gives you a pedestrian offset zone, which is under the hood surface, a certain surface which has to be clear from any obstruction, so that in the event of a dummy injury or the head injury, there should be some sufficient kind of absorption zone or energy absorption zone that should be available, which should be free from any hard obstructions. So any hard obstruction is actually it's an energy dissipating device. The mannequin can, the pedestrian can hit that zone, and there can be a severe damage to the heads of the pedestrians. So CAVA also gives this pedestrian surface, which technically looks like this one. So it is very important for underbody engineers to know this surface, because they should not allow their suspension towers or maybe any kind of NVH stays on the underbody or the engine bay area. They should not cross these limits always. It should always stay beneath that level, so that there's ample room from the top side for the energy absorption. CAVA also protects this feature for the active hood geometry here. The first video we saw was actually it was the active hinge on the hood, but this also function can be deployed with the help of windshield airbag here. So there are two functions to deploy active hood. One is active hinge, and then the airbag deployments directly here. So active hood capability or active hood function can be simulated in CAVA. Yeah, exterior safety radius, as you know, the exterior of the vehicle is actually regulated by due to minimum safety radius on the exterior panels and bumpers, etc. So ECR 26 is the standard which specifies all these requirements for uh, exteriors. So Kava can Kava can check your cast geometry or maybe engineered geometry, and it can check for different locations. Whatever green dots you see is actually tested locations for the sphere, and they are found to be compliant. Whichever you see red here are actually non-compliant zone. So having this information is of great importance, because knowing this can really give scope to re-engineer these areas. Maybe this area can be slightly lower down, or size can be lowered, so that judgments and decisions can be taken right in the digital phase only. Yeah. In the interiors, we have similar requirement for head impact zones, minimum radius requirements on the bump for the hood and not, not hood, but the dashboard and the door trims also on the A pillar. So Kava can generate, it can give a reference zones. It can give you head impact zone for the driver and passengers, as you see on the right side images. And it can also takes care of the excluded area. It's called steering offset, of steering wheel offset, and it can also create a LIP directly on the dashboard. This line is the level of instrument panel, what you see running from here. So everything above is under purview of the head impact, and anything below is actually a knee form, or the knee injury criteria applies to the lower zones. So Kava can certify your dashboard areas which are sometimes quite critical and quite intricate details are there in the IP, which needs to be certified quite efficiently and quite well, so that we don't see any surprises. Because based on this feedback only, we go ahead for the CAS finalization and CAS confirmations, and we then start our trims engineering accordingly. Just like interiors, we apart from in many other regulations on the seat, like seat belt anchorage and seat belt strength, head strength, etc. There is a minimum requirement, minimum radius requirement on the seat also, which is regulated by EC R17 number regulation. So it divides the seat into three zones, 1, 2, and 3. And for all the three areas, there are certain minimum radius criteria that needs to be met. So Kava can take your seat geometry, the whole seat geometry, and it can certify whether your seat geometry does meet the CCR 17 or not. Yeah. Knee form, as I said, below the level of instrument panel is actually under purview of the knee impact zone. So knee impactor is actually, there's a two methods, knee impactor of the straight way and the inclined way. Both methods can be used for the checking. So as you see, whatever black spots are, uh, they are they are valid points, but they are not touch-worthy points. Whatever points you see green are compliant points, and there are certain amount of red points here which are touchable and which are not under, which is not following certain radius parameters. So naturally, these are the action items. The cockpit engineers can refer these and forward there and do their design modifications accordingly to make it. And they can also suggest the styling team also to correct the designs here or to correct the surfaces here. Last is actually Kava Viper module. I think we are at the last module of the Kava. Kava has a Viper application which can simulate your Viper wiping calculations directly on the windshield. So it can simulate your different type of blades and geometries. For example, there's a standard blade which is found on almost every cars, and there are some trapezoidal and 4-bar linkage Viper arms also there, and some parallel arms are also there. So Kava can take any geometry or any type of Viper arm, and it can simulate your geometries of Viper. So it certifies your Viper designs, and you can then if it is not meeting, then you can really think of increasing your blade length or increasing your arm length or something like that, and you can then meet these certain criteria of Viper regulations. So here we see there's another feature. CAVA goes quite deep inside wiper calculations, and it can also check the wiping. It can also predict your wiping quality also. Now, wiping quality depends upon certain, it's called attack angle, which is mentioned here. So attack angle is something that the axis of the wiper blade and the normal axis to the windshield. So that angular deviation is called attack angle. Technically, it should be zero, but due to glass geometry or the windshield geometry, keeping it same also is not really possible due to curvature of the glass. So there is a limit that how far we can deviate from the zero on the attack angle. And if you see all the red points here, they are actually deviated that angle, which means that there can be such conditions where the wiper blade can twist really badly in that area, and that means it will not wipe properly the glass there. So these areas should be properly checked, that what are our attack angles and etc. So CAVA can give you very a heat map kind of thing, where you can pictorially see which areas are not being wiped correctly. So if unfortunately if any area is directly in the FOV zone, then we have to take extra care for that, and make the corrections in the attack angle or maybe in the geometry of the windshield. I think that was the last function from CAVA Viper. Let's take who globally and in India use CAVA. Mostly all European car makers and American car makers do use CAVA for their day in day out activities in architecture area. And also in India, we have a lot many customers, lot many big players who are our customers for CAVA, doing a lot of things in CAVA for from architecture to certifications and etc. So they want to be double sure that when they face the certification, they should not face any surprises in the certification stage, because if something goes wrong in the certification stage, then that's calls for a extremely time delay that can impact your vehicle launches. And if it is due to the supplier mistakes or something, then it can really the OEMs can really impose a big penalty also due to their they can't meet their planned launches. So as I said in the very first title, that regulations are critical. They should be done with the utmost care. They need high skilled manpower to carry out this. But CAVA resolved all this with this tool, so you need not worry about this all, and this all risk is taken by CAVA itself to certify digitally everything on the go. So Mahindra is our customer in India. There are many customers in India who use CAVA day in day out. However, you see many big names are there. You have Audi, BMW, Ford, Mercedes, Skoda. They are all. Volvo is also a global customer for CAVA. So CAVA is very popular in Europe, and it's getting extremely high momentum in India, because we have to serve the customer really fast. Nothing can be more good if we get the CAS today of the front bumper, and within a couple of days we provide the CAS feedback to the OEM immediately with the help of CAVA. Nothing can be more fast and more efficient than this. So CAVA provide that opportunity window to provide extremely fast feedback to the OEMs. Thereby, there are chances of winning the programs quite early because of the efficiencies. Yeah, I think with this, I am at the end of the presentation. So I now hand over to Mr. Satyam Pandey, who is our colleague from EDS Bangalore, who would show you a fantastic demo of CAVA application directly here. So over to you, Satyam.
Thank you for the wonderful presentation, sir. So I hope my screen is visible for everyone.
Yes.
Can I get some? Yeah. So now I'm beginning with the CAVA demonstrations. So this is a typical CATIA which we have. I think people who are using CATIA, they well aware of it. Then here we have the something called start. So in the start, we have in the infrastructure we have CAVA vehicle architectures. So the moment if I'll click on that, so it will take me into CAVA, for example, here. Now I'm clicking here. So now first thing first, when in the presentation, when I explain you, see we have the CAVA, and in order to go to the CAVA, we have seen how we have switched the window. And once we have switched the window, we have something called insert. And once you click on the insert, we have the couple of options of CAVA tools. Following with the OVA, that is the overall vehicle architectures, then the mannequin, visions, safety, wiper, and the reports tools and schedules. So here we have something called OVA. In the OVA, we have something called base data. A base data is a set of parameters where we add all those loading parameters, the vehicle wheels parameters, seating parameters, and the category of the type of vehicle it is. The moment if I'm clicking on the base data, so you can see here by the click of button is creating one baseline, and here you can see the vehicle category. Now, for example, I have off-road and limousines. So now I'm selecting as a limousine, or I can give any vehicle name descriptions, for example, CAVA demo, and then I can change the vehicle width angle, the overhang front and back. So there's something I can change here, and then again I can give here the vehicle wheels definite details. Now, for example, I want to see where is my wheel exactly lying if I'm making any change on it. So I can click here in the visualization. So I want to show by the wire and the face. So I can just click on that, or I can go with the points as well. Yeah. And then furthermore, if I want to edit any parameters with respect to my static radius, then diameter, width for the wheel camber, for example, in and out, for toe in, toe out. So any degree I want to make, basically we see for industrial vehicle, for example, tractors or the pickups loads, they have something called camber in, camber out. So where we can add here also the wheel to see, analyze the further details. So further with that, we have here seating geometry, seating details. So seat here we have to select the seat, the SRP seat points. So if you have the seat point, you can select, or you can simply put the coordinate here. For example, if I'm putting 115, let's say minus 116, and then 170. And I can just click on the button. I can add it here somewhere. You can see it's been created here, and nonetheless, I can if I know my proper seat reference points, I can just create by these values. And then same if I don't have the seat points, or I can go with the heel reference point, seat wheel center points, and the paddle reference points. Along with that, further we have the edge point travels. So what are the travel length is there in X directions? So it's something I can define the extra travel length, and the angle, torso angles, or the seat angles, which we have here. We can do it. If it's the fixed, then we can mark it as a fix. Further to that, we have the individual type. Now, whether it's a type of individual seat or it's a bench seat, there's something again I can select here. So, and this is for the driver. Further, if you want to add the passengers, so again you can add the passenger for the front as well as for the back by defining the again the your uh, by putting the coordinate of the seat SRP point, or maybe by selecting the SRP point like this, which I'm selecting now. So it's automatically selecting as SRP points. And the orientations is the front road, back road, left, right corner, all is the customs. Then following with the loading parameters. So now here we have the loading parameters. If you have the vehicle grid path, curve mass or design mass, or gross vehicle mass, or empty loadings, or with respect to the different standards. It could be your FMVSS, it could be your MLIT, or it could be your ADR. So those parameters you can define it, or EC. Yeah. Then if you have your own parameters, for example, you have your own company parameters. So we have something called user defined loading. You can add it here. So once you have done with these things, you just have to click OK, and your base data will be ready. So that's simple it is. So I'm just closing this because I have already opened some session with me. So you can see here, I have one session with me where I have defined every parameters which is required. So in this demonstration, I'm going to showcase the couple of safety as well as for the wiper examples. in how it's calculated in CAVA. So here in the insert we have something called safety, and the safety we have something called safety radius and safety tools, and along with the partial quotations which we have seen in the presentations. And now, for example, I want to do the safety radius. I click on the safety radius. Yeah. So so I hope my screen is visible to everyone, right?
Yes, yes, Satyam.
Yeah. So now further, I'll give the input parameters. Once I click on the safety, you see one dialog box has been pop up, and in this dialog box, first thing first, you have to define your uh, base data. Select your base data which we have created, and the standards. We have the various standards. So as of now, for example, if I want to do ECER 26 or ECER generic 2.5, so where the speed radius which would be 2.5. Now, for example, here we have the radius check and do the bumper check. So I want to click on the bumper check as well. And then here we have to put the parameters, put the input parameters, and your input parameters will be your bumper, for example, here bumper. And now once I'll select the bumper, you see it's automatically selecting. Here, or along with that, I have to tell the cover that it's a front bumper, and I want to do the radius checks as well, and the invertations, whether it should be always pointing towards the camera where the continuum is going to drop. Now, for example, I'll change the invert, and then I'll just click apply here. Yeah. Similarly for my beams also, like for my grills also. So I'll just simply turn on my grill. So simply I'll select my grill as well, and again here I'll give the treatment here from general to grill, and this would be a front bumper, and then I'll check the invert, so it's pointing towards the camera. So again, I'll add it here. Now, for example, I added here, I want to check whether everything has been sure or not. So we have something called to surface orientations to check the orientations whether it's correct or not. And then I can run the surface orientation here as well. So you can see now all the camera is pointing towards all the points are pointing towards the camera, which are the good. If is there any false would be there, it will come away from the camera. So just click OK. And once I've done that, I'll just simply click apply. So it will hardly take 2 minutes to analyze, or less than 2 minutes to analyze the entire the bumper. Also, you have seen the precision which I have kept. I kept it on 50%. The number of precision if I reduce, the lesser time it's going to take to iterate the process. So yeah, you can see it's completed with a fraction of minutes. And you can see if in the presentation also you have seen when we are talking about the safety, where we have seen the green area and the area which was not reachable as a black, or the area which is violating the safety into the red. So similarly here you can also see some of the area just here. So you can see some of the violated area, and some of all the green points you can see is the pass area, and the red points you can see here is is where the surface radius is not passing. And similarly, if you want to analyze those checks, for example, to check what are the results has been passed or failed, here we have something called results. So in the results, I can analyze for my bumper as well as for my safety radius or the radius checks. So you can see if I'm going to my safety radius checks, so it's completed 47,092 points, and out of which it's violating 427, and the sharp edges are the 16, and the unreachable zone are 23,859. So unreachable zone, which is are not reachable, but it is whenever if I want to check, I can check it. It will be always come under the certainly in the pass area, because yeah. And then further is for the bumper. Here in the bumper, it's calculated 47,116 out of 890 were the numbers violated below the minimum radius checks, and the again its violated points would be the 16 sharp edges. Yeah, and 23,859 where checks has been unreachable zone has been done. So we can see only the difference where we can see here the violating the minimum points. Here we getting 427, here we getting 89. So rest assured. Further, if I want to check each of those violated point, I can go to the violated points. So you can see here, and I can click on the radius. I can get the lower value or higher value as per my requirement. So you can see now if I'm seeing which has the least value, so I can click here, and then again I can click here, and what I can do, I can frame on, or I can show the devices. I have options. Now for example, I can create the section also, or maybe show sections, or I can drop the devices. So now for example, here I will drop the devices. So you can see this is the point where the device has been dropped. So you can see here now, and I can create the section also. So sections. So now I can check the sections, and after clicking the source section, I can see it in the section viewer. You can see the values. Furthermore, now for example, it has a 2, and I can here again I can what I can do, I can show the devices simply. Yeah, you can see this is, and then here also I can show the section, and I can see in the section viewer what the values. Section viewer. So I'll just change it. So because I already calculated for 2, so in the point I can see 2 values. So I'll just click on the 32, and then it will change to this value. And you can see here, it's doing for the 2-point checks here, where it's showing the gap value of 2, and the gap size is 36, and for the R1 and R2. Yeah. So I'll just click close this here. Similarly, you can do one thing. Suppose you want to check only the unreachable, or you want to check only the violated point or the sharp edges. So we have something called in the visualizations. If I go here, and I can do one thing. I can go into the bumper and radius. So I'll just go for the bumper and radius. I can just hide all those things here. Similarly, I'll go for the bumper also and hide those things. So now I just want to check the sharp edges and the area which is has violated. So I'll just apply here. So I can easily you can maneuver now my geometry and see where the violated points are there, and I can easily check now details smoothly, because the rest of the things where the area were passing, the only thing area was not passing on these lines where it's a violated point or the sharp edges, the red ones. Yeah. Now, for example, I don't want, like suppose again I'm going to the violated point. I'm not sure which point is lining which one. So seamlessly check this point. Now, for example, I want to check this point or this point. So I can just go into the something we have interactive check. I can go into the interactive check, and then I can click here on the start. And the start, I can just here what I can do. I just want to snap it as a grid. Yeah, and now I want to create as a section also, and the show devices when I click. So now for example, I'm clicking here somewhere here. So now you can see I can able to easily create the devices from here also, or maybe I can just want to check this one, or somewhere I want to check this one. So I can easily drop a device and create the section as well. Furthermore, I want to check in the section viewer. I can click here, for example, show section now, and now I can see interactive checkpoints. So you can see this checkpoints. Now this checkpoints further. Yeah. So I can zoom in and check this point. Now further, I can check this point, and I can change the direction as well. Now, for example, it's an upward directions, or I want to check in the X direction, or make it as auto directions. So similarly, I can check with this also. Yeah. And then I can take it as a snap, or I can create it as a report. Now, for example, uh, this is for the interactive check. I'll stop this one. Yeah. Now, for example, if I If I want to go again to the volatility point and I want to create as a report, I can just simply here click here and just select all the points which I have. I'll just select all the points immediately. So you can see all the validated point has been selected, and then I can create as a CSV file, export to the CSV. So now this file will be exported as a CSV file. So for the report purpose, in order to generate the report, I can create as a CSV file, or I can do one thing. Suppose if there is a one users are there, he does not use this cover, and I want to transfer these points, and I want to transfer this peers or something. I can just simply click. I can just click OK, and then I can do one thing. And now I can here I'll go into the insert and export. So I want to export this tool to the non Kava users or the users which want to send to detail. So I can select this report. Now, for example, I've created this one, and then I have options to export the entire set of geometry also and the particular feature also. So I want to export only the visible data here. I don't want entire detail which I have calculated. So I'll just click here and export this. Yeah. So you can see this is this is where whatever the export feature has been created here. But suppose if you want to export this feature in a particular set of geometry, that we have option here, and I can select somewhere here or somewhere any other bumper area, and I can export to that particular set of geometry as well. So now, for example, if I close this, let's say I'll hide this. So whatever the points are coming at the exported point, I can see here. I can see all the points. I can see the devices, measurement devices 3, and I can hide this, unhide this, or I can edit this file for the particular report generation. Yeah, just hide this as well. So this was with respect to the safety radius. Yeah. Now further we'll see one more analysis with respect to the safety for the seat minimum radius checks. Now we oftenly check the seats, check whether the seats any sharp edges are there or not. That's something we do the analysis. So for that we have something called safety and the safety radius, and we have two options like in interior minimum radius checks and seat minimum radius checks. Interior radius checks and seat. This is for the specifically with respect to the seat. I'll just click on the seat. Again here we will click on the the bumper the base data, and after selecting the base data, again we have the the ECR 17 or any further if you are adding the standard area. As of now, I have the ECR, and I want to do the these radius check, or I want to create the seat impact area. So in the in the presentation which was showcased by Shishi sir earlier, where he was addressing the impact area 1, 2, 3 in the color coded. Similarly, what you can simulate here. Now, for example, I don't want to create as a the impact area. I just want to check the seat radius. So because in order to complete this earliest as possible, and so I'll just select this. Yeah. So now I'll select the geometry. Right, and I'll check the orientation. It's pointing away from the camera. I'll change the orientation and mark as a seat and add it. Similarly, I can select the rest of the geometry, and this is pointing again away from the camera. I'll change the orientation and add this. I'll add this. And similarly, I'll add the header also. So we have the headrest or something. So if your headrest is integrated with the seat, we have on the top options, you can see we are selecting for the driver seat. So here we have option called seat with integrated headrest. So as of now, our seat is not integrated with the headrest. So I'm just selecting as a separate and check the seat, and I'll select this, add this. So now all the geometry has been added, and further one thing I have to check the seat, the surface orientation. I can go here Now somewhere I made some wrong orientation, so I can explain you that also for you. So I'll just click here, wrong orientation, on the orientation check. Again, I'll click. So now you can see here, one is pointing away from the camera. That's something I have to rectify here. And now I can again check this one. For example. Or maybe I can just do this. Nonetheless, it's fine. I'm just going to start the simulation because I'll just apply it. It will again. It's running on the good accuracy of 50%, and within a couple of minutes, less than a minute, it's going to finish the iteration for the analysis for the sheet for the sheet itself. So similarly, what you have seen on the bumper, this the pendulum, the spear dropping test. So similarly, you can see on the for the seat interior also, where you drop the pendulum and check is there any issue is there or not, or whether it's violating the pendulum points. So if any kind of violation is there, again it will going to mark as a red with respect to the standards. So yeah. So now you can see here again the green areas and the yellow areas and the some of the red areas and the black areas. So what you can see in the black area, which is unreachable zones, but that zone it doesn't has the what do you call it, violated or the sharp edges on it. So it should be considered as a safe. And then further here again I can see the results, what are the checks has been done. So I can see here I have skipped this area, seat impact area. I have skipped the test, and only the what I have done the seat radius checks, where 1 lakh 5,026 points has been checked. Out of it, 1,790 were the minimum radius checks, and 2,038 points were the sharp edges, and 87,000 were unreachable. So out of which again I can go to the violated point, and similarly what I can do here, similarly I can export the point which I require. For example, I want this point, or I can export into a CSV file, or I can export the faces I want. For that I can export that as well also. Now again here I can go here visualization, and I can hide the save zones, for example, which is reaching by sphere. And yeah, I can just click on the point which is below the minimum radius. I'll just click apply, so it will be easy to find you. Yeah, so again you can see here, and similarly again I can go to the violated points. Now for example, if I'm clicking the point, you can see which point I'm clicking here, it's showing here. And then again I can do one thing, show devices. So now you can see here this device has been dropped here. And then furthermore again I can show this section, and I can again here show into the section where I can check this point. Yeah. So similarly here I can go for the interactive check as well, and analyze here for my seat easily, without any without having any issue with respect to the points which I want to use it. So I can continuously check each and every by creating this pair continuously here, as the same what we have done for the bumper here. So it was that simple to analyze these things. So I'm just clicking OK. Now this is done for the safety. Now I want to show you something for the vision, or maybe for the wiper analysis. I'll just minimize this. And now you can see here we have another geometry here where I have the windshield of three-wheeler and the wiper. Yeah. So now for example here again I'm going to in the insert, and the insert we have the visions, and the vision we have the field of view. Now I want to check the field of view. Based on the field of view, I want to check my wiper analysis, so that I should know that a wiper area is passing the regulation, the norm which I want to check. So now, for example, here we have the EU 2021 for the wiper. So I can just check on, and I can select the base data again, and I can select the screen here, and you can see I can check the daylight curves also if I want, and you can see the wiper, the A field and B field which is created here. On offers, for example, there is some cases where company has their own norms and regulation, or as per the our AIS also, like we can add the AIS regulation inside this cover also. Or not, for example, let's suppose you have some regulation which is different. I can click here free, and I can change the detail which I needed. Now I can give my own custom value with respect to the standards and check further detail which I need. So I'm not creating this again field of view, which I have created again here already. Now I'll just do the wiper analysis. So you can see here wiper, we have created the points, the driving axis, the plate points. Yeah, so again, I'll go to the insert, and here we have the tool wiper. Once I click on the wiper, so a dialog box will pop up again here. And here we have the base data. I'll just select the base data, and I have the couple of standards here. So now we can see ADR, US FMVSS. So now I'm going with the 21 because the FOB which I have created is for the same. So I'm just clicking here, field of view. I can just click on the field of view. And if you don't have the field of view, either way you can select the entire entire your windshield. So number of wiper you has, type of wiper you have. Now, for example, standards, the type of driving axis you have, standard trapezoid, or parallel arm. So that's something you can simulate here. And then further here we have to define the axis. Like for example, I'm going for the standard, so I'll select my axis. So my driving axis I selected here, and then I'll give my starting angle. And so now I'll similarly I'll do one thing here. I'll give my parameters for the starting angle and the ending angle for my values. So here I'm just changing my values and the orientation from where the wiping area is happening. It could be happen from left to right or right to left. If you have if you have two wipers, then both the wipers is functioning differently. That is something orientation you can add here. So I'm just quickly giving this value so we can finish this, because we are also running out of time. So I'll just start the angle. I'll just put is 110 degree, and the angle would be 120. I'll just keep, and then here I'll go, and I can check my demo angle also. So demo angle is something where it will create the another wiping 2D diagram to check whether how the demo angle is forming or how this current blade is happening. So I'll just click here, and then I'll check here details, like for example now folding axis. So I'll just select my folding axis. Yeah, I'll just click on the keep link so it will be remembered. And then further I'll go for my blade. Yes, select my blade as well. So I'll select my blade axis as well, and then I'll give them my height value. So these are the height of mine. So for example, my height is 35, and the lower length is 220 to 300. For example, I'm just going to the random value now. So I'll just click apply, and you can see some for wiper is out of the kinematic range. So suppose if it's out of the kinematic limits, the wiper will automatically reconfigure, CAVA will automatically reconfigure it, and it will tell you the what are the currently available range, and then based on that it will show you the wiping area. So further than, if you want to edit this parameter, now for example I want to edit this parameter, so similarly I can go again. Now for example again I can go here and again change my value if I want. So now here I'm going and I'm changing my value, and I'll just simply apply. So now moment if I am applying, I can see now the values are different. So here also I can change my differences. Now for example I can click again on the start angle. Let's say I want to create my start angle as 117 to let's say I want to 180, and I'll apply. So you can see now the entire range is taking into the account, and apart from that, it is also covering the field of A and field of B. Yeah, and then furthermore, you can visualize your values with respect to grid points, color mapping, and you can showcase your value also. So show value and apply again. So you can see the value will occur here. What each and every instances, what are the degree of values is giving, and then further in the output you can check your wiping conditions. Now different wipers you have. So I have only one wiper. I want to show the lines, and I want to see the folding axis, normal deviations, and I want to see the normal deviation with respect to vertical direction of the blade. I can check that, or horizontal weight, or the trajectory of curves. Like for example, we have created the five instances, so each curves how much the trajectory has been happening. So that's something I can analyze here, and further I can save this as a generate report and save it as a report, and later on I can use it. Yeah, so I'm just clicking OK. So this was it for the demonstrations. Yeah. Now any questions, then please let me know. Now we'll move to the Q&A session. Sushil sir, over to you.
Yeah, I'm presenting my screen now. I hope the demonstration was really interesting. So let me see if you see my screen. Is my screen visible?
Not yet.
Not yet. Can anyone please make me presenter in that case? Aniket, are you there?
Yeah. You are now presenter, sir.
So, okay, so now I think we are at the end of our session. So I would like to thank Mr. Sushil, Mr. Satyam, and Mr. Chandrakant for their insightful insights on the Kava. And so I'm very confident that it was very helpful for our audience today. I also would like to thank our audience for taking their time out and joining this session. So if you have any further queries related to the subject matter or any other requirement, you can always connect with us, or our details are displayed on the screen right now. You can reach out to us at any time and we would be happy to address your queries. Please do keep an eye on our upcoming webinars and seminars. You can follow us on our social media. So thank you everyone.